So welcome to the lecture. So we have discussed quite a bit about a general PQ rank tensor in previous few lectures. For example, 0, 1 rank tensor, which we call one form, and we denote it by omega, and in terms of component and basis, then write it as omega nu dx. As usual, we are going to use the coordinate basis. This is known as one form. Now let us consider an example of 0, 2 rank tensor, which is antisymmetric. So let's take an example of Maxwell field strength. So this is a 0, 2 rank tensor, which has a component which denoted by F mu nu. This is the field strength. The basis dx mu, tensor product dx mu. And from electrodynamics, we know that this is antisymmetric. That means mu nu equal to F mu nu. Now let's try to rewrite this equation in the following way. F equal to F okay. This is trivial, but we know that this is equal to minus F mu nu. So we get the following. Half note that this mu nu indices contracted with this mu nu indices. So they are dummy indices. So I can relevel them. So I can call this mu as mu and this mu as mu index. In that case, we can take this F mu nu common and have dx mu its product dx nu minus dx nu its product. Now this antisymmetric combination of these two coordinate differential forms a basis for this antisymmetric tensor. In particular, we can introduce the following symbol for this antisymmetry combination, which we'll call a wedge product. Dx mu wedge dx mu. This symbol is known as wedge product, which is nothing but the antisymmetric combination of these two elements. Again, remember this is a Cartesian product, which means they are product. And you can see because these are antisymmetric, when mu equal to mu, it will vanish. And they form a basis for the antisymmetric tensors. Because this is antisymmetric, if this would have been a symmetric, then anyway it will vanish. So this will have a non-vanishing component which will be antisymmetric in mu indices. And that is the case for Maxwell Feldstrom. And in terms of this wedge product basis, we can write the AF as F. I'm going to write half, but then I'm just going to replace it by 2 factorial, which is same. You will see the reason. Then mu dx mu wedge dx. And this entity is known as a 2 form. Because it involves 2 of the basis elements of one form in an antisymmetrized form. Now we can generalize it for 3 basis elements. Let's say we take dx mu wedge dx nu wedge dx rho and write down the antisymmetrized combination of them. What will be there? One term will be dx tensor product dx nu dx rho, and all the cyclic combination will come with a plus sign. So we'll have dx rho dx nu dx nu plus dx nu. So mu. So the cyclic combination mu goes to nu goes to, and when you interchange any of the 2 index, which are the non-cyclic combination, will come with a minus sign, and there will be 3 such elements. One of them will be dx nu next one will be dx rho dx nu wedge dx nu, and then there is the last one, which is basically dx nu wedge rho wedge dx nu. So this is a totally antisymmetrized combination. Then in terms of this antisymmetric basis, we can write down 3 form which takes the following form. Let's call this H. We'll have 3 factorial H mu rho mu wedge mu wedge. Because this is completely antisymmetricist, is H mu rho, this component better be totally antisymmetric. Because if this is a symmetric part, we'll just not contribute. Symmetric times the antisymmetric part and all the indices contracted vanish. You know it from elementary matrix multiplications. So this is totally symmetric. That means it's antisymmetric on all 3 indices, and this is known as a 3 form. And now you can see the pattern. You can generalize it. And now you also see that by written 1 over 2 factorial for the 2 form, because for the 3 form you have a 3 factorial, right? So total number of these term involved in this wedge product is basically 6, 3 factorial, right? And so on. So you can generalize it for higher forms. So one example of this is something called Ramond field strength that you encounter in string theory. We leave that to you to explore more. And just like Maxwell case, you know that Maxwell field strength can be written from gauge potential MUs, and then you take derivative of these MUs, then you can construct the Maxwell field strength. Similarly, there is a gauge potential for this 3-form Karl-Raimond field, which takes the following: B mu nu dx mu. So this serves as a gauge potential for this H, and this is sometimes also known as Nevill-Schwarz defect. Gauge for H field. Now, in general, under Lorentz transformation, these totally antisymmetric tensors does not mix with their symmetric part. Lorentz transformation cannot change the symmetric or antisymmetric properties of the tensors. It is very easy to check. You should do that by yourself. Hence, the P forms constitute a subspace in the vector space of zero comma P rank tensors. And we denote that subspace as omega. This is the space of P forms. And if you work in D+1 dimensional space-time, then the dimension of this subspace omega P, nothing but P+1. This is the binomial coefficient dimension of now you can see that in D+1 dimensional space time you can have at most D+1 forms. For example, if you consider 3+1 dimensional Minkowski space time, you cannot have more than 4 forms. For example, in 3+1 dimension, if you try to write down 5 form, which takes, let's say, the basis of this, right? So the 5 form will have a basis of this form, but you know each of these mu, nu, rho, sigma, tau index takes only 4 values, 0, 1, 2, 3. But this is totally antisymmetric. So remember our discussion about Levi beta tensors. So if you try to write down this kind of elements involving 5 of these differential, then in 3+1 dimension, at least 2 of the index will take the same value. Hence, by antisymmetry, it will vanish. So you can have at most 4 form in 3+1. Now this differential form help us to set up an alternative to vector calculus in general space-time, irrespective of whether it's a flat space or curved space. And that is known as exterior calculus, which we'll discuss a bit in the next lecture. And using this differential form, you can write the physical laws in a very elegant way without bothering about underlying coordinate systems. So we'll also discuss about that a bit in the next 1 or 2 lecture. But at this point, I must say that due to historical inertia, especially in the context of classical gravity, people still use the usual covariant calculus, don't use that much this language of form. So keeping that in mind, in the second half of the course, we will focus mainly on the covariant calculus instead of using these differential forms. But if you are interested, we highly encourage you to look into these in more detail. Thank you for listening.